Good afternoon. Now we are handling today simple bending theory of simple bending or stresses in beams. Now already we have discussed in the previous class. In the class 18 we have discussed elaborately the behavior of beam, how the beam behaves. Now in this class I am discussing I'm recalling the things whatever we have discussed in the previous class in few slides, and then we'll proceed with some few problems. Let us solve few problems. Regularly, those who are in we are dealing with the theory of the simple bending. Theory of simple bending. So therefore, we know the beams are loaded. The beam. No, it is in horizontal member supported at the ends, and that depends. Now, elaborately, we have discussed about the beams in the bending moment and theory, the bending moment and shear force chapter in the equation. Second slide. We are discussing elaborately. We are discussed about the types of how the beam is. It is a horizontal load resisting member transferring the load to the support. So this is horizontal member loaded. When it is loaded, there will be a bending moment. That is deformation. It is the shape of the beam. It is exaggerated shape of the beam. Now beam will be like this. Now it is one example. I have taken that is exaggerated deformation. This is going to happen. This is one beam I have shown here. Now this is the beam, and this is the beam cross section. The beam cross section, and it is loaded. That is uniformly distributed loader. Now in the theory of simple bending, there are few assumptions. The assumptions are the material of the beam is perfectly homogeneous and isotropic. The beam material is thrust within the elastic limit, obeys the Hooke's law. Now already in our lecture series I have discussed about this. The material of the beam is perfectly homogeneous and isotropic. Now material is made up of uniform throughout the beam, and the load transfer is also uniform. Now that is one assumption. Now strictly speaking, sometimes it may not be possible in practical, but theoretically it is assumed. And the beam material is thrust. In the beam material is thrust within the elastic limit and obeys the Hooke's law. The Hooke's law is thrust is proportional to strain. The next one is the most important thing we should the assumptions is the beam is made up of number of layers. Beam is made up of number of layers, and each layer are independent either to contract or expand. Depending upon the load condition, depending upon the deformation. Now, for example, now let us consider a beam loaded, and it is assumed that the beam is made out of number of layers. It is made out of number of layers. Now these are the layers. Now this is this is the layer above. These are the layers. Beam is made out of number of layers. And when the beam is loaded, this is the deformed shape of the beam. This is the deformed shape. When the deformation takes place, now here the bottom layer is suffering from tension, and the topmost layer is suffering from compression. When we reach, now these are the layers. There are various layers. Now these layers are independent to expand or contract. This is the assumption made in the theory of simple bending. So here in this theory, the most important thing one should understand is, now see here, the beam is made out of number of layers. There are many number of layers. The top layer, this layer is suffering from maximum compression. That is shortening. The length of this is the original length of the beam member layer, and this is the compressed layer. The same layer compressed, and the length of this layer is shortened. That means it is resisting the compression. Isn't it? Now, when you reach the next layer, it is less. Now, the expansion, the compression is little less than this. Now, when you reach again, when you come down below, the layers are the compression, the shortening of these layers get reduced. And again, this is the original layer. Now, this is the original layer. And when you go down, when you move downward, this layer is suffering from tension. That is elongated. This layer is elongated, and this layer is much more elongated. This is much more elongated, and this layer is maximum elongated. Now, therefore, all these layers are suffering from tension. Now, when the material B material is stressed, elongation, subjected to tension, they are suffering from tension. Now, all these layers are suffering from compression. Therefore, all these layers, the third assumption is that each layer is independent to expand or contract. Now, whereas this is another layer, one layer, this is no expansion or no contraction taking place here. No expansion or no contraction. Whereas the layers above this layer, this is the one layer, central layer, this layer. So above this, all the layers are suffering from compression, and below this layer, all the layers are suffering from tension. Now, therefore, all these layers are subjected to tensile force. Now, therefore, they are suffering from tension. Is it not? The stress induced in these layers are tensile stresses. Whereas in the this layer, this layer has no tension or no compression, no expansion or that is shortening. Now, therefore, above layers are suffering from compression. This is suffering from the maximum compression, and this is suffering from the maximum tension. Now, therefore, now the beam is stressed within the elastic limit, and this stress, the maximum stress is in this layer, compressive load, compressive stress, and this layer is suffering from maximum tensile stress. Is it not? Now, this is the third assumption. The independent, all these layers, the beam is made out of number of layers. When it is subjected to a load, now when it deforms, now these layers, all these layers independent to that is expansion or that is contraction. Is it not? And again, now another assumption, the value of Young's modulus. The value of Young's modulus is same in all the layers, either in tension or compression. The Young's modulus remains same. The Young's modulus remains same. And also another assumption made in this theory is before bending, the beam cross section is plane. The beam cross section is plane before bending. Even after bending also, the beam cross section remains plane. So these are the assumptions made in the theory of simple bending. And this is a theory. Whatever the things I have discussed, it is mentioned here. It is all those other whatever the things we have discussed. These things are written here. Now, similarly, again continuation of that. Now, I want to mention again one more thing in there. Now here, we have discussed. Now see, this layer, no expansion or no contraction. Above these layers are suffering from compression. Below these layers are suffering from tension, expansion. Therefore, these layers are subjected to tensile stresses. Above this, all the layers are subjected to that is compressive stress. Now, whereas this layer, no tension, no expansion or no shortening. Now, this is called neutral axis. Now, neutral axis means the stress in this layer is zero. Is it not? Now, this layer is called neutral axis. Now, this layer is neutral axis means You know, no expansion or no tension. You know, this length is equal to the length, that is original length of this layer. Now, therefore, this layer is called, this R dash S dash layer is called neutral axis, isn't it? Now, this is the theory, whatever the things we have discussed. Now, I explain, know that they are written here. Now, as and when you find time, you can go through this. Yeah. And you know, in the theory, in bending theory, now whatever now we have discussed, how the based on the discussion. Now you see we are now this is the stress diagram. This is the that is shear stress diagram. This is the stress diagram. Now this is one that is now the topmost layer is suffering from compression. Now this is the compression, and the bottommost layer is suffering from, that is, tension. Now, when you go towards the center, now here the stress is zero. Now, this is the neutral axis, where the stress is neutral axis, isn't it? Now, this is called the stress diagram. Now, this is how. Now, that is why, see now, instead of making a rectangular beam because zero stress is available at this point. Therefore, the material is less in this portion, isn't it? The maximum stress at the compression, we have made this, that is maximum section required according to the compression. Now here bottom, again, according to the according to the tensile stress available, the section is made. Now in this region, this is minimum section is required. Therefore, now we are saving the material of this portion. This portion is material saved. And similarly, now this is the stress diagram. This is again stress diagram. Now this is a rectangular hollow section. This is a rectangular hollow section. Again, now here this is hollow part because we need less section here because zero stress is occurs. So stress is zero here. We need maximum, that is maximum material here. Therefore, now in this portion less stress and zero stress. Therefore, no, this is the savings in the material. That is the advantage of this simple bending theory and the stress diagram, isn't it? And these are the various sections which are being used in our construction practice, isn't it? And now here the most important thing is the beam is when the beam is loaded, the beam deforms. The beam deforms, and a bending moment is induced. Bending moment, due to the application of load, it deforms. That means a bending moment is induced in the beam. And this is the length of the this is the length of the beam. Now it is one this is one portion of the beam you have taken, that is delta x. Now here the bending moment and the stress in the layer. Now the stress in the layer, it is F. In some textbook it is written as FB, that is fiber stress. Now, or somebody will call this as skin stress. Now someone will call this as bending stress. No, isn't it? No, whatever may be. Now here M is the bending moment in kilonewton meter due to the application of the load, and F is the stress in each layer. Layer stress, and Y is the distance from the neutral axis. Y is the distance from the neutral axis. From the neutral axis, when you reach this point, the stress will be less. When you go, the stress will be more. Stress increases when you move toward that is topmost layer. Similarly, when you reach downward, that is we reach at the end the maximum tensile stress, isn't it? Now this Y represents the distance from the neutral axis. Now we can find out the neutral stress in the layer, in any layer. We can find out the stress induced in each layer, and Y is the distance to the layer from the neutral axis, and R is that is radius of curvature, the beam bends through which, isn't it? And this I is the moment of inertia. That is M is the bending moment, F is that is fiber stress or skin stress. Somebody will write this as F suffix B, isn't it? And Y is the distance from the neutral axis, and R is the radius of curvature of the beam bends. This is the radius of curvature R. And so, and I is the moment of inertia. I is the moment of inertia of the section. Now, section, that is the cross section of this beam is rectangular or any shape, maybe circular, hollow, I section, whatever may be. Now, moment of inertia. I is the moment of inertia. Moment of inertia in millimeter to the power of 4. Now, in this, to solve, to understand the bending theory, we must know exactly the bending moment and shear flow diagram, and also we should know the moment of inertia. Isn't that? Already we have discussed elaborately about these two. We have addressed these two chapters. That is bending moment and shear force. Also the moment of inertia. We have discussed. You in length. No, please kindly go through that. Then we will let us solve the few problems in this. Isn't it? So this is the these are the terms used in bending theory. Isn't it? Now see, and E is the Young's modulus of the material in Newton per millimeter square. Now this is the bending equation. This is the major equation, bending equation. M by I is equal to F by Y is equal to E by R. Now this is called bending equation. Isn't it? Now M is the moment of bending moment, I is the moment of inertia, and F is the fiber stress, and Y is the distance of the layer from the neutral axis, and E is the Young's modulus of the material, and R is the radius of curvature through which the beam bends. Isn't it? Now one should remember that bending equation. Isn't it? Now bending equation, it is not derivation is not included in our syllabus. Anyhow, that is I mentioned. Now how the equation arrived, M by I is equal to F by Y is equal to E by R. How it has been arrived, it is shown here. Isn't it? If you find time, you can go through this. Isn't it? Now next slide please. The continuation of that is the equation, that is bending equation. How to derive the bending equation? Now we can do that. Isn't it? We can go through this. You can find out how to get that equation, that is bending equation, that is M by I is equal to F by Y is equal to E by R. Isn't it? And again, this is the bending equation. Already we have discussed about this. So yeah. Now this is the moment of resistance. Moment of resistance. When you take a section, now how to find out the moment of resistance? Now from the bending equation, see, from the bending equation, moment of resistance, that is moment of resistance is equal to, that is M by I is equal to F by Y is equal to E by R. That is the bending equation. See, that is M by I is equal to F by Y is equal to E by R is the bending equation. From this equation, now whatever we need, depending upon the data available, depending upon the necessity, we can take either these two equations, either these two terms, or we can take these two terms, or we can take this term and this term. According to our convenience, we can take and solve the problems depending upon the necessity. Now here, the moment of resistance, it is M by M. M is the moment of resistance. Now always the moment of resistance is equal to bending moment. The bending moment occurs due to the bending moment occurs due to the load applied, isn't it? Now the moment of resistance is induced in the beam section depending upon how the beam is, isn't it? So therefore, now the moment of resistance is the resistance developed by the material due to its cross section, isn't it? And bending moment is the induced in the material due to the application of load. Always we must equate the bending moment and the moment of resistance. Bending moment is acting in this direction, that is the due to the load, and the bending different deforms. But the beam we have to design in such a way that we have to induce the resistance in the opposite direction. Now therefore, the bending moment is always must be equal to the bending, that is moment of resistance. Isn't it? and section modulus. The section modulus, from that equation, m by I is equal to f by y is equal to e by r. Now we will take these two terms, that is m by I is equal to f by y. And let us transfer this from one side to the other side, that is m, let's keep the m, send the I the right side, then we will get m is equal to I by y into f. Now therefore, this m by m, this m is equal to I by y into f. Now here, that is m is equal to I by y is equal to z. Now this is called modulus of section. Modulus of section. No, this is that is from modulus of section. Modulus of section means sometimes it will be asked in the examination for 1 or 2 marks. What is the modulus of section? For modulus of section, now we must write, isn't it? Now I by y, z is equal to I by y, and z is known as the modulus of section. Modulus of section, isn't it? Now, in our last previous class, now we have solved few problems. Now, how to find out the modulus of section for different sections, like rectangular section, that is hollow rectangular section, circular section, and also the hollow circular section. Now we have derived. You please go through and refer those guys, those slides, isn't it? So therefore, now when you need to calculate the moment of section modulus is equal to I by y. I is the bending moment. For rectangular section, it is equal to BDQ by 12. We know that. And y is the distance from the neutral axis. Now normally we consider it is d by 2, half of the distance. That is section d, depth d, and d by 2 is the maximum. That is the farthest layer. That is the topmost layer or the bottommost layer. So therefore, that becomes BD square by 6. And for other section also, we have discussed in the previous class. You please kindly refer those slides, isn't it? And now let us solve a few problems. Now in this problem, a steel rod 120 mm dia is bent to a circular section. Find the minimum radius of curvature to which it should be bent, so that stress in steel is not to exceed 120 newtons per millimeter square, and given that is E is equal to 2 into 10 to the power of 5 newtons per millimeter square. Isn't that? Now therefore, what our students should do, first write down the given data. Write down the given data carefully. Then bring the equation m by I is equal to f by y is equal to e by r. Then m by I is equal to f by y is equal to e by r. From that, depending upon the data given, now select any two terms. Isn't it? Now for this given section, for this given problem, now let us take this, that is f by y is equal to e by r. We need to calculate the radius of curvature. The beam can be bent, isn't it? The steel rod can be bent. We need to find out the radius of curvature r. And therefore, now f by y, substitute the values, given values. Now just to transfer this, send this e this side, and r is equal to, that is e by, that is r is equal to, that is r is, you just send this side, and substitute the values, will get, that is 10 to the power of 5. Now because for the data given here, the data are given. Now you just substitute and we can calculate that is, d is given, diameter is given. Therefore, when you consider the diameter, y is equal to d by 2, that is, it is a circular section. It is 120 millimeter. Half of this will be that is the y. Y is the farthest distance, isn't it? So therefore, substitute the values. We can calculate the radius of curvature. The rod can be bent, isn't it? So similarly, now we can solve one. Let us solve one more problem. That is a rectangular beam 300 millimeter deep is simply supported over a span of 4 meters. What UDL the beam may carry if the bending stress is not to exceed 120 newtons per millimeter square, and I is equal to 8 into 10 to the power of 7 millimeter to the power of 4. Now these are the data given here. Now the given data, that is depth of the beam is given. It is 300 millimeter. length of the beam is given, it is 4 meter, and F stress in the beam is equal to, that is 120 Newton per millimeter square. And also it is given I is equal to moment of inertia of the given beam. The beam section is 8 into 10 to the power of 7. Now therefore, now first let us call this, now let us take this, that is bending equation. From the bending equation, now depending upon the data given and what we need to find out, now they have asked to calculate the, that is, what is the, in the problem, what is the UDL, what is the load on the beam. Now they have asked to calculate, or they have asked to calculate the what is the load on the uniformly distributed load. What is the uniformly distributed load can be, or loaded can be applied on the given section, isn't it? So therefore, we know that. So take this equation, that is bending moment. This is the bending moment, moment of inertia, and stress in the beam, and this is the, that is the y is the farthest distance of the layer from the neutral axis, isn't it? Now we need to, let us consider only these two terms. Now this is one term and another term. Let us make use of this term, isn't it? So we know that now already we have discussed in length about the how to calculate the bending moment and how to draw the bending moment on Chapter diagram. Now therefore from this, now let us assume that W kilonewton per meter is the load can be applied for this beam, isn't it? We don't know. Now let us assume that W is the W kilonewton per meter load is the load can be what is not assumed, isn't it? Now therefore, now let us calculate all the data and substitute to this. Now we will get the what is the load, isn't it? Now therefore, we know that is M by I is equal to F by Y is F by Y. Now therefore, let us calculate the bending moment first. So to calculate the bending moment first, what we should do is not bending moment. It is WL square by 8. WL square by 8 is the bending moment. Bending moment, maximum bending moment at the center. Now for the UDL, for this condition, for this beam, WL square by 8 is the bending moment. Is it not? Now first calculate the bending moment. That is WL square by 8. And I is given. They have given the I. That is moment of inertia. Moment of inertia along the x-axis, isn't it? That is the maximum x-axis. They have given I is equal to BDQ by 12. If they have not given, so if the section is given, we have to we need to calculate. Now whereas directly they is given, therefore so let us substitute I is equal to, and also F is equal to stress in the material. Stress in the material is given as 120 Newton per millimeter. Substitute here, and Y is the distance depth, that is depth of the section beam is given. From this, now D is equal to Y by 2. Y is equal to D by 2. Now therefore Y is equal to D by 2. It is the farthest distance from the neutral axis. Now therefore, just substitute this. Now we will get the value of W, that is kilonewton per meter. Isn't it? Now see the continuation of the problem. First calculate the bending moment. That is WL square by 8. WL square by 8, and bending moment is equal to W. That is substitute this value, the given value. Substitute the given value. Now we will get the bending moment is equal to so much W Newton millimeter. Isn't it? And you know, again, please, MR is equal to, that is moment of resistance equal to, that is Z into F. Z is equal to I by Y. It is I by Y into F. I is given, that is I is equal to I is equal to moment of inertia is given. Y is equal to, we have calculated here, it is 1 to substitute here, then we will get the value of moment of resistance, isn't it? And you know, now bending moment is equal to moment of resistance. Moment of resistance is equal to bending moment. Equal these two, then the only unknown here is W. Therefore, we will get W. W will be the load on the beam. That 32 Newton per millimeter it can be loaded on the given beam. Isn't it? Similarly, in the one more problem let us solve here. Now it is given that a simply supported beam of span 5 meter is 150 millimeter into 300 millimeter in cross section. The given cross section is, that is 150 into, that is 150 millimeter into 300 millimeter is the the rectangular cross section, find the UDL that can be safely allowed on the beam when the bending stress is limited to, that is 125 Newton per millimeter square. Write on the given data carefully. That is length of the beam. It is L is equal to 5 meters. That is 5000 millimeter. And depth is given. D is equal to 300 millimeter. And breadth of the beam is given as 150 millimeter. And similarly, the given stress, the stress given, stress in the material is, that is 125 newtons per millimeter square. Now we need to find out what is the UDL W. This is not load. What is the load on the beam? We need to calculate this. Now first write down this equation, that is bending equation. M by I is equal to F by Y is equal to E by R. This is not. And we know that moment of resistance is equal to, that is bending moment. This is not. So first calculate in the how we have calculated in the previous problem. Bending moment is equal to, now take these two terms. Now these two terms, M by I is equal to F by Y is equal to F by Y. Now M is equal to moment of inertia is equal to, sorry, bending moment is equal to W L square by 8. W L square by 8 is the bending moment for the given loading, for the given beam and for the given loading. Isn't that? Now I is the moment of inertia. I is the moment of inertia. Now we need to calculate the moment of inertia. How to calculate the moment of inertia for the given rectangular section? For the given rectangular section, moment of inertia can be calculated as VdQ by 12. It is a rectangular section. For the rectangular section, let us calculate VdQ by 12. VdQ by 12. And F is the stress they are given here. This is not 125 Newton per millimeter square. And Y is the, that is D by 2. No, 300 depth is given. Therefore, D by 2 Y is equal to, that is the farthest layer from the neutral axis to the farthest. That is the last layer. This is not either top layer or at the bottom layer. Now Y is equal to D by 2. Now substitute all the values and then again please go back. Substitute all the values. No, definitely we can. No, it will give you the moment of resistance is equal to bending moment, and therefore now substitute the value. The only W is unknown. We can calculate. No, is it not? Please go back. Yeah, one slide please. Yeah. Now see, if you substitute and calculate this, now you will get 19 Newton per millimeter. 19 Newton per millimeter. That is very simple. Now we can solve this. Isn't it? Next problem. Again, a 4 meter long beam with a cross section of 120 mm width and 200 depth is simply supported at its end, carries a UDL of 4 kN per meter. Find the maximum bending stress developed in the material. Now we need to calculate the stress induced in the material. This is not. To find out the stress induced in the material, what we need to do, now write down the given data first. Write the given data. V is equal to 120 millimeter and L is equal to 4 meter and depth D is equal to 200 millimeter. The given data, these are the given data, and W is given, that is load acting on the beam, UDL. UDL is equal to 4000 Newton per meter. Now we need to calculate the stress. Now therefore, for the given loading, bending moment is equal to WL square by 8. That is W is given, it is 4, is not 4 into L is L square, 4 L square, substitute the values and we will get, that is 8 kilonewton meter, or that is equal to 8 into 10 Newton millimeter. And the MR, that is moment of resistance for the given beam, is equal to Z into F. Z is, that is I by Y. I is equal to VdQ by 12 and Y is equal to D by 2. This is the section modulus. V square, straight away we can substitute this and multiply by the, and this is the only unknown, and now moment of resistance is equal to bending moment. Therefore, now bring this value, substitute for moment of resistance. Now substitute this, we will get the stress in the beam. Stress in the beam. Isn't it? Now this is a simple problem, but don't forget the equation, that is bending equation. M by I is equal to F by Y is equal to E by R. Isn't it? So let us solve one more problem. You will see. Okay. Now see, a timber beam freely supported 6 meters apart. It carries a UDL of 12 kN per meter. If the stress in the timber is not to exceed 8 newtons per millimeter square. Design a suitable section making the depth twice the width. Now here again, in this problem, a timber beam is really supported 6 meters apart. The span is given, isn't it? 6 meter span carries a UDL of 12 kilonewton per meter. The load applied is 12 kilonewton. Stressing the timber beam is not to exceed 8 newtons per millimeter square. Design a suitable section making the depth twice the width. For the given problem, we need to find out what is the size of the beam required to carry this load, isn't it? Now, therefore, compute, first write down the given data. L is given, stress is given, and load is given, that is 12 newtons per meter, 12 newton per meter, and then we need to calculate depth is equal to, and depth, what is the depth and what is the breadth of the beam. Now first let us calculate the bending moment. First calculate the bending moment. To calculate the bending moment, we know that is for the UDL, WL square by 8. WL square by 8. Substitute the values W and L. Substitute the values. Now this is the bending moment. The bending moment in the beam due to the load. Is not the load applied. And we know, let us calculate, that is MR, and that is moment of resistance is equal to ZF from the bending equation. From the bending equation, here moment of resistance is equal to bending moment. Therefore, substitute the value here, and Z is equal to BD square by 6. That is Z is equal to I by Y. Z is equal to I by Y, I BDQ by 12, and Z by I, Y is equal to D by 2. Now here, for the given problem, making the depth twice the width, that is breadth is B, depth is D. Now we must do, that is, here in the substitution B is equal to, that is B is equal to 0.5 D, or D is equal to 2B. Now this is the given data. No, I have not written here, it is missing here. Now kindly make a note, that is making the depth twice the width. Making the depth twice the width. So that means B is equal to, now here it is B and this is D is equal to 2B, or that is B is equal to 0.5 D, isn't it? Whatever may be, you take anything, you can substitute whatever you wish to do it. Now for here, BDQ by 12. Now D is equal to 2B. Substitute the value of 2B. Now this is 2B. B into 2B square. That is BD square divided by 6 into stress is 8. Isn't it? Therefore, we will get the value in terms of 32 B cube. 32 B cube by 6. Isn't it? And we know that the bending moment is equal to moment of resistance. Therefore, 54 into 10 to the power of 6 is, now we will get that is B value. Now cube root we will get it. Now simplify this, we will get B is equal to 217 millimeter. Now that we say that is B is equal to 220 millimeter, and depth, that is 2B multiplied by 2 will get, that is 4 kilometer. This is 4 part. This is a very simple problem. Now we can solve this. Now few problems I will solve on the board. You will just go through that. Now I will do it. Isn't that? The next problem, that is, now a timber beam of rectangular section 60 mm wide and 120 mm deep. Find the section modulus. Now it's a very simple problem. Just this one small note, like now it will be asked. Sometimes it will be asked in multi-choice questions. So therefore, that is Z is equal to, that is R. Z is equal to I by Y. I is BDQ by 12 and Y is equal to D by 2. Now we will get this much, isn't it? And we will solve the one problem. Now that's in the board. A timber beam 6 meter long. A timber beam 6 meter long. A timber beam 6 meter long. This is the 6 meter long beam. Subject 6 meter long. a timber beam, 6 meter long, freely supported at its ends. It carries a UDL of 20 kilonewton per meter. That is 20 kilonewton. This is the UDL. 20 kilonewton. It is 20. So it is 6 meter span. 6 meter span. 6 meter span. Subject to a load of 20 kilonewton per meter. You know, so the beam section, the given section is B, and this B. B is equal to 2B is given. 2B. That is twice the. So to solve this problem, so the beam is the given a 6 meter span beam is subjected to a UDL of 20 kilonewton per meter, and the beam section is B, and the depth is 2B. So they want to calculate the design a suitable section making the depth twice the width. In the stressing timber is not to exceed 8 newtons per millimeter square. So this is the problem given. So see, the stress is given as stress is equal to, that is 8 newtons per millimeter square. 8 newtons per millimeter square. So first let us calculate. Let us know the given data. Now first let us calculate the bending moment. Now bending moment is equal to W L square by 8. W L square by 8. W L square by 8. So W is 20 into 60 square divided by 8. So this is the bending moment. Bending moment. Now it is kilonewton meter, and we know that is Z is equal to moment of resistance. Moment of resistance is equal to Z into F. So here Z is equal to, now here Z is equal to, that is I by Y. I by Y. Therefore I by Y is equal to, it is B dq divided by 4. B dq by 4. B dq by 12 divided by, it is D by 2. D by 2 is Y. I by Y. Now here B red and D is equal to 2B. 2B cube divided by 12 divided by, it is 2B divided by 2. 2B divided by 2. Now you have substitute the values. Substitute the values, and you know that is MR is equal equal to moment of resistance is equal to bending moment. Equate the moment of resistance is equal to bending moment. Therefore, moment of resistance MR, moment of resistance is equal to, that is bending moment. Now bending moment we have calculated here, W square by 8. Now MR is equal to, that is these calculations available. Substitute this, the only unknown here is, that is B. Now find out B. Now simplify this and you will get the breadth B. And breadth B is equal to, according to the data given, breadth B, now D is equal to 2B. Now therefore, now you're making the value, what is the result we are going to get it? Now the result, so this is the, we will get the B. B is equal to how much? B is equal to, we are going to get 256 millimeter, 256 millimeter, and that is equal to, say, it is 260 millimeter, and D is equal to B, depth of the beam. Depth of the beam is equal to, it is 2B, and therefore it is 2 into 260 is equal to 520 millimeter. 520. Hello. Yes. Hello. 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 For the given problem, the problem is given. It is 6-meter span subjected to a point load of 60 kilonewton per meter. 60 kilonewton per meter. Now we need to design the beam to carry this load. The making the section, that is breadth B and depth D. Now they have given the relation for breadth and depth. It is B and it is D. Now D is equal to 2B. That is the relation they have given. Now for this, now we have to find out the value for B and also D. Now for that, now we know that. Now first let us find out. Now after it is given, the stress is given. That is stress in the material is equal to, it is 120 newtons per millimeter square. That is stress in the timber beam is given as 8 newtons per millimeter square. So this is the problem given. Now we need to calculate the bending. We need to calculate the, that is the B and D, that is the size of the beam for to resist this load. Now therefore, now first let us calculate the bending moment. Bending moment is equal to, it is WL square by 8. WL square by 8. Now W is given. W is equal to 20 kilonewton and multiplied by, it is L. L is 6 meter. 6 meter. 6 square divided by 8. So this is the value of the bending moment due to the load. And also we need, let us calculate the moment of resistance, MR, moment of resistance is equal to, it is, that is Z into F. So moment of resistance, now here Z is equal to, I by Y. Z is equal to I by Y multiplied by the stress. Now that is equal to, that is I is equal to B D cube by 12. D cube divided by 12. B D cube by 12. So Y is equal to Y. Y is equal to, it is D by 2. D by 2. So whereas here, now we know that now the relationship is given between the breadth and depth. Therefore, now let us substitute the value of depth. Depth is equal to 2b. Now let us substitute here. Now, therefore, how much you are going to get it here? It is b, and b is equal to 2 into 2 multiplied by, that is b, 2b cube divided by 12. The whole thing divided by d is equal to, again here, it is 2b divided by 2. Now, this gives you, now simplify this, now we will get some value and equate these two, bending moment and also the moment of resistance. Equate this and simplify the only unknown. We will get d is equal to under cube root. We will get the value for the cube root. D is equal to, now d, so from this, by equating bending moment and the moment of resistance, now we will get the value of, that is, the value is B is equal to the breadth of the beam. B is, after solving this, now simplifying this, we are going to get B is equal to 256.5 millimeter. 256.5 millimeter. 5 millimeter, and this is equal to, it is saying 460 millimeter. Let us round it up. Therefore, depth D is equal to 2 into 260, and that is equal to 520 millimeter. Now that is the, this is the solution. This is the, now our problem is solved. Then we will let us solve one more problem. Now, one more problem. One more problem. A floor carrying a load of 6 kilonewton per meter square. A floor. Now, a floor, that is a room floor. A floor carrying a load of 6 kilonewton. Isn't it? 6 kilonewton per meter square area. Isn't it? 6 kilonewton per meter square area. A floor carrying a load of 6 kilonewton per meter square is supported on a timber joist. No, that is timber beam. Supported on timber beam. That is, floor is supported. No, this is the below the floor. No, these are the beams. That is, these are the beams. That is timber beam. Timber joist means timber beam. The section of this beam is like this. So they have given the section of the floor beam. The beam size they have given. The beam size is 100 millimeter. So it is B is equal to 100 millimeter. And depth D is equal to 400 millimeter. They have given 400 millimeter. So the beam over a span of 4 meters. That is, from here to here, it is 4 meter. It is 4 meter span. 4 meter. The beams are placed 4 meters span over a span, and above this there is a floor. The floor is carrying a load of 6 kilonewton per meter square. Calculate the spacing of the beam if the bending stress is not to exceed 10 newtons per millimeter square. So that, see, now we need to calculate the distance between the each beam, that is spacing of the beam. Now this beam, from one beam. At a distance x meter from one beam to the other beam. And above this, above the beam, there is a floor, and the floor is loaded. Floor is loaded with 6 kilonewton per meter. Now, if you take a cross section, now the floor will be like this. Now this is the floor. The floor is like this, and the beams are placed. Now these are the beams. Now these are the beams. So this is the floor. Now please understand the problem. It is the floor, and these are the beams. Beam. Now this is beam. Beam. It is subjected to a load of, that is floor area over the floor. It is 6 kilonewton per meter square. Isn't that? Now this is the beam given, the beam size. Now we need to calculate the spacing of the beam from one beam to the other beam. That is x. And from this is again x. We need to calculate this x. What is the distance x? Now first what we should do, now we have to convert this load. We have to convert this load into, that is convert the load into UDL. So therefore, now let us consider the one beam. Now this beam. Now this beam is subjected to a load of half of this area. Now this entire area, this load is taken by this beam. Now therefore, load on the beam, total load on the beam is equal to total load on the beam. Total load on the beam is equal to area. Area is x distance. Now because center to center it is x. This area is 4 into x. 4 multiplied by x meter. 4 meter into x meter is the area. Now therefore, that is the total load is the intensity of the load per meter square. That is 6 kilograms. Therefore, it is 24 x kilonewton load is acting on the beam. That is, there are now I have written 1, 2, 3 beam. In the 3 beam, I have taken one beam. And in one beam, the load acting, that is one beam, the load taken by this one beam is equal to 24. Because now this area is the load. This load is load taken by this beam. So therefore, total load. Now this total load acting 24x is the total load acting on the beam. Now let me convert this total load into uniformly distributed load. Now therefore, now what we should do, that is UDL on beam, UDL on beam is equal to UDL on beam is equal to total load divided by the length of the beam. Length of the beam is equal to, now that is equal to total load is 24 into x. 24 into x is the total load acting on the beam, this entire beam. Now to convert this into UDL, that is length is 4 meter, that is 4. Therefore, 6x is the load acting on the beam, kilonewton per meter. That is 4 meter divided by total load is 24x is the total load, because we don't know the distance between the beams. No, this is one beam, this is another beam. We don't know the distance. Therefore, load acting is half of the load is acting on this beam, half of the load is acting on this beam. Therefore, we have taken this half. That is again x. Now this distance is again x. Now this is x. X distance x. So therefore 6 kilonewton per meter. Now we have calculated the UDL. Now after calculating the UDL, the next stage is, that is, now let us calculate the bending moment. To calculate the bending moment is equal to WL square by 8. WL square by 8. Now therefore, now what is how do you that is now we have calculated. Now this is the support. This is 4 meter beam. Then the load is acting. Now this is equal to it is 6x kilonewton per meter. So we have converted the floor load into UDM. Now WBM is equal to W square by 8. Now W is 6x. 6x into 4 square. Length is 4. That is span. The span of the beam. So it is divided by 8. So therefore, after simplifying this, so this becomes, so this cancels and we will get with, so remains with 2 is equal to 1228. It is 12x, 12x kilonewton meter, 12x kilonewton meter is the bending moment of the beam. And you know, now let us calculate the moment of resistance of the beam. MR, moment of resistance, is equal to Z into F is equal to Z into F. Now this Z is equal to I by Y. Z is equal to I by Y and multiplied by F, isn't it? That is equal to I VDQ by 12, BDQ by 12. The section is given B into D, isn't it? B into D, that is 100 into 400 cube divided by 12. Divided by 12. This Y is equal to divided by Y divided by Y is equal to D by 2. D means it is 400 divided by 2. So the whole thing multiplied by the stress. Now the stress is given as, now in the problem it is given the stress is limited to, that is 10 newtons per millimeter square into 10. Now MR is equal to moment of resistance is equal to moment of resistance is equal to bending moment. Bending moment. Now so equating this, now this is 12 x in kilonewton meter, that is equal to 12 x into 10 to the power of 6 Newton millimeter. So suppose equate this and this, so we'll get the value for the only unknown here. No, here only unknown is x. Now therefore x is equal to, now after having this we are going to get x is equal to, that is, next please, x will get, that is 2, 2, 2.2 millimeter. That is spacing of the beam, isn't it? Spacing, that is 22 centimeter. The spacing of the wooden beam, that is from one beam to the other beam, the distance is, that is 2, 2, 2 millimeter, isn't it? Now that is how we can solve the problem. Very simple analysis, simple problem, simple analysis. And let us solve one more problem of a similar kind. Now, the similar problem, similar type, with different data. A timber joist, a timber joist, 10 meter has to carry a brick wall. A timber joist means timber beam. A timber joist spanning 10 meter. That is, it is the spanning, the beam is 10 meter long, 10 meter span. The beam, it is a timber beam. It is a timber beam supported at the ends, and loaded with a brick wall, carrying a brick wall. The brick wall 20 mm thick and 4 meter height. The beam is loaded with a brick wall. So this is a brick wall. Brick wall. So this is brick wall. Brick wall loaded on the beam. So this is 10 meter span beam. 10 meter. 10 meter span and loaded with a 4 meter height. 4 meter, and the section is, the section of this wall is, it is 20, 200 millimeter, 200 millimeter. The thickness of the wall is 200 millimeter. This is the wall. Wall thickness is 200 millimeter, and this is the wall height. Wall height. This is not 10 meter span. The weight of the brick wall, brick weight, brick weight is given as, that is 19 kilonewton per meter cube. That is the brick weight, unit weight of the brick. 1 meter cube of brick weight, 19 kilonewton. And the permissible stress in timber is 8 newtons per millimeter square. This is not permissible stress in the steel, in the beam is, that is F is given as 8 newtons per millimeter square. 8 newtons per millimeter square. Permissible stress. Design a suitable section of the, or design a section of the joist in such a way that the depth of the joist is twice its width. Again, now see, this is the beam. This is the beam. Now let us find out what is the minimum beam size required. Now let us assume that, that is, this is the size of the beam joist. It is B, and they have given a relation. It is B is equal to 2B. L 2B. The breadth is B and depth is 2B. They are given. And the density of the unit weight of the brick wall is given, and stress in the beam is given. Now we need to calculate the, what is the size of the beam required, isn't it, to carry this load. So therefore, how to calculate this? First, now let us convert this UDL, the brick wall, into UDL, isn't it? First, let us convert this. Once if we convert this, our problem is solved, isn't it? Now this is 10 meter, and what is the load? Load on the beam, that is UDL. Now we have to find out what is the UDL of the beam. To find out the UDL of the beam, first let us calculate the volume of brickwork. Volume of brickwork, volume of brickwork. Brickwork is equal to, volume of brickwork is equal to, it is 10 meter multiplied by, that is 4 meter height multiplied by thickness, it is 0.2 meter, 0.2 meter. Therefore, it comes to, it is 40 into, it is 8 cubic meter, it is meter cube, 8 meter cube. It gives rise to 8 cubic meter concrete, 8 meter cube brickwork. Therefore, weight of brick is equal to weight of brick wall. Weight of brick wall is equal to, that is density multiplied by volume. Therefore, is equal to, how much it gives? It is 90 multiplied by 8. So therefore, 92 kilonewton. 92 kilonewton is the load acting on the beam. Now, to convert this into UDL, therefore UDL on beam, UDL on beam, brick joist, on timber joist, UDL on timber joist, timber beam is equal to, that is 92 divided by 10 meter. That is, so the entire load, this 92 kilonewton is acting over the 10 meter. Therefore, divided by 10. That gives rise to, it is 9.2 kilonewton per meter. So 9.2 kilonewton. Now our problem is almost solved. Now, therefore, after calculating this 9 point, that is the UDL on beam, now the UDL acting on the beam is equal to 9.2 kilonewton per meter. Kilonewton per meter. Now, therefore, that is, now let us calculate the bending moment. Bending moment. Bending moment is equal to, it is W L square by 8. Now therefore W is how much? W is the load acting on, that is UDL. That is 9.2 into 10 square divided by 8. Now this is the value we are going to get it. Newton meter, Newton meter, Newton meter, Newton meter. This is the bending moment. And similarly, now let us calculate the moment of resistance. Moment of resistance is equal to, that is Z into M. So Z is equal to I by Y. I by Y into M. Now therefore, I by Y. I by Y is equal to, how we calculate the I by Y? It is BD cube by 12. BD cube by 12. BD cube by 12. And this Y is equal to D by 2. D by 2. And the whole thing multiplied by the stress, isn't it? And this is equal to, now let us substitute this here. It is B, and D is equal to 2B, 2B square, 2B square divided by 12, and the whole thing divided by, it is B is equal to 2B divided by 2, and this is, the whole thing is multiplied by the stress. Now simplify this. Now that is again we'll get in terms of, simplify this and equate it to bending moment. Then we'll get, that is B is equal to, that is B is equal to, B is the answer. So we're going to get, we'll get B is equal to, that is 32.9 millimeter. It is 32.9 millimeter. B is equal to, B is equal to 32.9 millimeter. Say it is 33 millimeter, 33, 330, 330. We are going to get 329 millimeter, 330, 329 millimeter, and say it is 330 millimeter, 330 millimeter. And therefore, depth is equal to, depth D is equal to 2 times the breadth. Therefore, it is 2 into 330 is equal to 660 millimeter. This is what we are going to get it, isn't it? Now, still there are many problems. We can solve the problems in the similar manner. Now, this is the one more problem. This in the similar way we can calculate, and also, now this is the solution available with our PowerPoint. And similarly, now we have many more problems. Yeah, one more problem we have, like there are many number of problems available. Now, please kindly go through this problem and solve this. Now, in the similar manner, nothing, no extra, nothing extra is here. Now, I request you to go through this. And we have another, the most important thing in, that is beam of uniform section and beam of uniform strength, beam of uniform cross section, and beam of uniform strength. So let me discuss in 2 minutes, and beam of uniform strength and beam of uniform cross section. Cross section. So for cantilever beams, so beam of uniform strength. See the one cantilever beam. I think our people may have observed the section in the construction. Now we can see in the cantilever beam, the beam will be constructed like this. Beam will be constructed. And if you draw the bending moment for this, the bending moment will be maximum at the support and 0 at the end. So this is the BMD, bending moment diagram. Bending moment diagram. This is the bending moment diagram. This is the loaded cantilever beam. It is cantilever beam. Cantilever beam. And this is bending moment diagram. This is the section of the beam. Maybe sometimes it may be of RCC, or sometimes it may be of steel, whatever may be. So in the steel also, we'll reduce the section. So what I mean to say here, this is one loaded W below Newton per meter. This is the cantilever beam. It is a cantilever beam. For the cantilever beam, if we draw the bending moment diagram, the bending moment will be like this. Diagram will be like this. Now here zero bending moment, and here zero is their maximum bending moment. Now this is the bending moment diagram, bending with shape. Now this is the construction, maybe RCC beam. In front of your house, somebody may construct. Now this is the steel beam, steel truss or beam, whatever may be. Now see, now here zero bending moment, we need zero section, but we can't create the zero section. Therefore, what we will do, we will give minimum section here, and at the support, no, this is the maximum bending moment. Therefore, we will provide the maximum section. So therefore, now this is called beam of uniform strength, isn't it? Beam of uniform strength. Now, if you go to if you see an industrial shed, the shed will be like this. Now, the shed will be like this, and normally we will design the truss like this. Now, again, suppose if you draw a simply supported beam, bending moment diagram for a simply supported beam. Now, if it is loaded like this, if you load it, now the bending moment diagram will be like this. Now, if you draw the bending moment diagram, the VMD, it is the bending moment diagram, is VMD, and this is the truss. This is the truss. The truss will be done according to the bending moment. Here the maximum bending moment we have, therefore the maximum section we have here, maximum section. Now here zero bending moment, minimum section, zero bending moment, minimum section. Therefore, now this kind, now this is one example for beam of uniform strength. Beam of uniform strength. This is the beam of uniform strength. So this is another example for beam of strength, uniform strength. Now according to the bending moment, the section has been designed. So this is the bending moment diagram. The section is designed like this. So therefore, now this is the beam of uniform. Now your maximum bending moment, maximum bending moment, maximum section. Minimum bending moment, minimum section. Zero bending moment, minimum section. Now this is the beam of uniform strength. This is not beam of uniform. No, it is called beam of uniform strength. This is one example. This is another example. And the beam of cross section. For example, if you take an RCC building, in the RCC building, there are two supports. No, there is support here. There is another support, and it is loaded. What we will do? The beam will be constructed here. According to the beam will be like this. Isn't it? If you draw the bending moment diagram, the bending moment diagram will be in this. This is the bending moment diagram. This is BMD. This is the load diagram, and this is the RCC section. RCC section. RCC beam. RCC section or RCC beam. RCC. This is RCC beam. Bending moment diagram. Load, and this is the beam, RCC beam. Now what we normally will do, see here the maximum bending moment is maximum here. Here the bending moment is zero. Here minimum, the bending moment is minimum here. But at the time of construction, what we will do, we will design the section for the maximum bending moment, and we will provide the section throughout. It's not similar. Same thing we will do. So this is called beam of uniform section. Beam of uniform. Immediately of the bending moment, the section is designed for the maximum bending moment, and that will be constructed throughout the beam. So this is beam of uniform section, cross section. Beam of uniform cross section. So this is, if you take this, now this is the beam of uniform strength. Now according to the strength, the construction will be done. Zero bending moment, maximum bending moment, minimum section, maximum section. No, like there is RCC beam, beam, steel truss. Another example, that is a truss. That is a, suppose if you draw the bending moment for this kind of loading, now this is the maximum bending moment will occur. Therefore, what we will do? It is a steel truss. It is steel. steel truss. Accordingly, the system will be decided. This is the example for the beam of uniform, that is beam uniform strength, and this is the uniform cross. This is the beam of uniform cross. Now this completes the bending theory of bending. That is bending theory. Thank you very much for all the participants. Thank you so much. Thank you. Thank you.